Hello everyone, this is Artin, and today I would like to dive into a fascinating paper titled Retrieval-Augmented Generation for Knowledge-Intensive NLP Tasks by Patrick Lewis and colleagues from Facebook AI Research and several renowned universities. This study explores a novel approach to enhancing language models by integrating parametric and non-parametric memory systems. First, let us talk about parametric memory systems. These systems learn to represent knowledge through parameters of a model, typically neural networks. As the model is trained on a dataset, it adjusts in its internal parameters to store the learned information. This type of memory is static post-training, meaning it doesn't change unless the model is retrained. Examples include the weights in deep learning models like BART or GPT. On the other hand, we have non-parametric memory systems. These systems store information externally and do not rely on the model's parameters. Non-parametric systems can dynamically incorporate new information by updating their external data stores without retraining the model. A typical example is a database or an indexed retrieval system like the dense passage retriever used in RAG models, which retrieves information relevant to a given query in real time. Both types of memories have their unique strengths and are often used together in advanced models to leverage the flexibility of non-parametric systems with the efficiency of parametric systems. This hybrid approach allows models to handle a wider range of tasks by combining deep learned insights with the ability to adapt to new information quickly. First of all, let's talk about pre-trained LMs. Pre-trained LMs are great. These models have fundamentally transformed how machines understand and generate human language, bringing numerous advantages to the field. Firstly, pre-trained language models leverage vast amount of data, training on diverse corpora sourced from books, articles, and websites across the internet. This extensive training enables the models to develop a rich understanding of language nuances, idioms, and even jargon from various domains. The benefit here is clear. Such models come pre-equipped with a broad knowledge base before they're even fine-tuned for specific tasks. Secondly, because they are pre-trained on such a wide range of texts, these models exhibit remarkable generalization capabilities. They can understand and generate language across different contexts and styles, making them incredibly versatile. This versatility is crucial for applications ranging from simple question answering to complex dialogue systems in virtual assistants. Another significant advantage is efficiency in deployment. Since the bulk of the model's training is done beforehand, adapting a pre-trained model to a specific task through fine-tuning requires relatively less data and computational resources compared to training a model from scratch. This not only saves time and energy, but also makes cutting-edge NLP accessible to organizations without the resources for extensive training operations. Moreover, pre-trained models often serve as a starting point for further research and development, acting as a baseline upon which novel architectures and techniques are built. They provide a foundation that accelerates innovation in the field, pushing the boundaries of what's possible in AI and machine learning. But there are also some limitations for these pre-trained large language models. While these models have brought significant advances to the field of NLP, they're not without their challenges. Firstly, one major limitation is their tendency to generate hallucinated or factually incorrect content. Despite being trained on extensive datasets, these models sometimes make errors in factual accuracy, particularly when generating content on topics not well represented in their training data. Another critical issue is the immense resource requirement for training these models. The computational power needed to train large-scale language models is substantial, which not only demands significant energy consumption, but also makes it less accessible for smaller organizations or researchers. Furthermore, pre-trained models often struggle with adapting to highly specialized or niche domains. They require significant fine-tuning with domain-specific data, which is not always feasible or available. Lastly, there are ethical concerns. The data used to train these models can contain biases, which the model then inadvertently learns and perpetuates. Addressing these biases is crucial to ensure fairness and impartiality in model applications. In summary, while pre-trained language models are powerful, they come with notable limitations that need careful considerations, especially when deploying them in critical or sensitive environments. Now let's talk about retrieval. In the realm of natural language processing, retrieval mechanisms play a pivotal role. These systems are designed to fetch externally stored knowledge or text, which proves invaluable across a spectrum of NLP tasks. First off, the ability of these systems to provide precise and accurate access to knowledge is great. This precision ensures that the information used to answer queries or solve problems is relevant and reliable. Moreover, updating this externally stored knowledge is straightforward at test time, allowing for continuous improvement and adaptation. A particularly exciting development in this field is dense retrieval. This approach is beginning to outshine traditional information retrieval methods, offering more nuanced and effective ways to sift through vast datasets. However, the applications of retrieval technologies isn't without its limitations. Typically, these systems require some form of retrieval supervision, which can complicate their implementation. Moreover, many rely on heuristics, methods like TF-IDF for fetching data, which might not always yield the best results. Also, another challenge lies in integrating these retrieval systems into downstream models, often necessitating task-specific adaptations to ensure they function correctly within broader applications. So, while retrieval systems are incredibly powerful, navigating their limitations is crucial for maximizing their effectiveness in real-world settings. Now let's get into what Retrieval-Augmented Generation or RAG is, which is the main topic for this paper. Retrieval-Augmented Generation or RAG seamlessly integrates retrieval and generation process for NLP tasks. RAG operates on a fundamental principle called latent retrieval, meaning it doesn't require labeled documents for its retrieval process. This is a game changer as it simplifies the preparation for datasets, making RAG applicable across any sequence-to-sequence task, enhancing its versatility. Now, what does RAG actually need to function? There are three key elements. First, a generator model, which could be any high-performance pre-trained model like BART, GPT-2, or T5. This is what generates our textual output. Second, a retrieval model, such as DeepPR or ICT, pre-trained to fetch relevant content based on our input queries, actually. And third, an expansive index knowledge base filled with diverse text documents like Wikipedia, web pages from Common Crawl, or even social media content like tweets. These components work in concert to create a system that not only retrieves accurate and relevant information, but also crafts coherent and contextually appropriate responses. This makes RAG exceptionally well suited for handling complex knowledge-intensive tasks where accuracy and depth of information are important. Here is what the architecture for RAG looks like. The RAG architecture begins by taking input text sequences. These are fed into our retrieval module. Within this module, a neural network processes the input sequence, encoding it into a compact query vector. This vector then undergoes a maximum inner product search, or MIPS, to locate and retrieve documents from our index document store. These documents are represented as vectors, and the ones selected have the highest .product scores relative to our query vector, indicating a strong relevance to the input query. Once the top K documents are identified based on their inner product scores with the query, they are forwarded to the generator module, which is powered by the BART model. The generator takes these documents and processes each one, effectively synthesizing and integrating the information they contain. It then produces a prediction for the output sequence based on each document. Finally, to arrive at our output sequence, we employ a technique called marginalization over these top K documents. This step aggregates the outputs generated from each document to produce a cohesive and contextually rich final sequence. This method ensures that our output not only captures the essence of the input, but is also enhanced by the most relevant external knowledge source during the retrieval process. In this paper, we explore two specialized configurations of RAG framework, which is the RAG sequence and the RAG token models. The RAG sequence model integrates retrieval into the generation process by maintaining a consistent context across the entire generated sequence. Here's how it works. When an input query is received, the model retrieves a set of documents that are most relevant to the query. These documents are then used as a stable, unchanging context throughout the generation process. The key here is consistency. The same set of documents informs the entire response, ensuring that the generated text is cohesive and contextually unified from start to finish. This model is particularly effective for tasks that require extended narratives or explanations, where maintaining thematic and factual consistency is crucial. On the other hand, we have RAG token model. Contrasting with the RAG sequence, the RAG token model allows for a more dynamic integration of retrieved information. Instead of using a single document set for the whole sequence, the RAG token model can use different documents for generating different parts of the output text. This is achieved by retrieving a document set for each token generated, making it possible to adapt the context dynamically as the generation unfolds. This method is incredibly useful for tasks that benefit from varied perspectives or detailed factual accuracy, such as generating content that requires weaving together multiple threads of information or answering complex questions that touch on diverse topics. Now let's discuss a crucial component of Retrieval-Augmented Generation Framework, the Dense Passage Retriever, or DPR. This innovative retriever is pivotal for enhancing our model's ability to access relevant and precise information quickly. The Dense Passage Retriever is specifically designed to fetch relevant text passages from a vast documents corpus. Unlike traditional retrieval methods that might rely on keyword matching, DPR works by converting both the query and potential passages into dense vector embeddings. These embeddings are then matched using dot product calculations to determine relevance. The beauty of this method lies in its ability to capture deeper semantic meanings rather than just superficial keyword overlaps, allowing for more accurate and contextually appropriate retrievals. DPR indeed has a crucial role in RAG. It directly influences the quality and relevance of the information that feeds into the generation process. By providing highly relevant data to the generator, DPR ensures that the output is not only factually accurate, but also richly informative. This capability is essential, especially in tasks that require precision and depth, such as answering complex questions or generating detailed explanations. DPR integrates seamlessly with both RAG sequence and RAG token models. And for RAG sequence, it retrieves a set of documents once per query, which are then used consistently throughout the generation. For RAG token, however, it retrieves potentially different sets of documents at each step of the generation process, allowing for dynamic adaptation based on the evolving needs of the text being generated. This flexibility makes DPR incredibly powerful across various types of NLP tasks, enhancing the model's adaptability and effectiveness. Let's get to the next important component of this paper, which is the generator. That is BART actually. BART, or bidirectional and autoregressive transformers, serves as the generator in our RAG models. It's a powerful seg-to-seg model pre-trained using a diverse range of text sources. In the RAG framework, BART's primary role is to take the retrieved documents provided by the dense passage retriever and generate the final text output. It does this by integrating the context provided by these documents into a coherent and contextually rich narratives or answer. BART is particularly effective due to its hybrid structure that combines both bidirectional context from transformers and autoregressive capabilities. This allows BART not only to understand the context better, but also to generate more fluent and accurate text sequences. In both RAG sequence and RAG token models, BART seamlessly processes the information retrieved by DPR, ensuring that the generated outputs are not just relevant, but also engaging and informative. This integration highlights the synergy between advanced retrieval techniques and cutting-edge generations methodologies in tackling complex NLP tasks. In sum, BART enhances the RAG models by providing a robust mechanism for transforming retrieved knowledge into articulate and precise language, crucial for the success of knowledge-intensive applications in NLP. Now let's get to the next section of this paper, which is about decoding part. In RAG models, decoding involves taking the generated predictions for each token or sequence from the BART model, which are informed by the top documents retrieved. The key to this process is the marginalization of predictions across these documents. Here are the two decoding strategies for the two models. For RAG sequence, decoding a single set of documents informs the entire sequence. The model uses a consensus from these documents to generate each part of the output, maintaining thematic consistency. On the other hand, RAG token decoding allows for dynamic adaptation by selecting different documents for different parts of the sequence. This is particularly useful for complex queries where different segments of the response may require information from various sources. The end result of this decoding process is a text output that is not only contextually enriched but also precisely aligned with the input query, which ensures both relevance and cohesiveness. As for the experiments part of this paper, in the exploration of retrieval-augmented generation models, they conducted a series of experiments to validate their effectiveness across various knowledge-intensive NLP tasks. Here are key conducted experiments. First one is open domain question answering, or OpenQA, in which they test RAG models on multiple data sets, including natural questions and trivia QA, comparing them against both baseline seg-to-seg models and other state-of-the-art retrieval systems. The other one is fact verification, in which RAG models were evaluated on their ability to verify factual statements using the Fever dataset, showcasing their precision in handling nuanced information. And the other one is Jeopardy question generation, in which they assess the model's capability to generate questions based on the provided answers, highlighting its creativity and accuracy in content generation. The experiments demonstrated that RAG models not only achieve state-of-the-art performance on several benchmarks, but also significantly outperform traditional seg-to-seg models, especially in tasks requiring deep factual knowledge and contextual understanding. So in our presentation, we have explored the dynamic capabilities of retrieval-augmented generation models, which integrate both parametric and non-parametric memories to enhance natural language processing. Our presentation has highlighted how RAG models not only achieve but set new benchmarks in state-of-the-art results for open domain question and answering tasks. A standout feature of RAG is its factual accuracy and specificity, which has been shown to be preferred over the output of purely parametric systems like BART. This preference underscores the practical value of RAG models in real-world applications, where precision is very important. Throughout the research, they conducted an extensive evaluation of the retrieval components embedded within RAG models, which affirms their crucial role in the model's performance. Now, looking ahead, there are some grounds for further research. One is the possibility of jointly pre-training the retrieval and generation components from scratch. This approach could potentially enhance the cohesion and efficiency of the models, leveraging objectives similar to those used in training BART. These findings open numerous avenues for future studies, particularly in exploring how parametric and non-parametric memories interact. Understanding this interaction deeper can lead us to more effective ways of combining these memories, promising significant advancements in a wide array of NLP tasks. And in conclusion, the RAG framework represents a significant leap forward in our quest to make machines understand and generate human language with unprecedented accuracy and relevance. Thanks a lot for watching this video, and I hope you enjoyed it.